Well, thank you very much, guys, for inviting me, and I hope this turns out to be an interesting presentation. Uh, for those of you who are active on 6 meters, there's been quite a bit of interesting propagation over the last week or so, and we'll talk about what that is when we get to the appropriate point. But it's frustrating because you have to be in the magic spot, the right place at the right time, and the openings tend to be short. But boy,
Mhm.
they can be pretty exciting if you're really a 6 meter guru. So this image is an image of my 6 meter Yagi. It's an 11 element Yagi on a 60-foot boom, and it's side mounted on a rotating tower that you can see here. It's a military tower known as an AB 105. So we're going to start out the presentation by cautioning you that if you're a 6 meter operator, just forget everything you know about HF propagation because to a very large degree, all of the expertise you've gained in HF propagation doesn't have a clear fit to the way propagation works on the 6 meter band. Things are really different. Sporadic E winds up being a very, very important mode for 6 meters, especially in June and July, but also at other parts of the year, especially at more northern latitudes in the United States. And F2 is also very important. Usually on 6 meters, we experience that in a mode of propagation that is commonly called trans-equatorial propagation, referred to briefly as TEP, but it's F2, just like we experience on the HF bands, except that it's enhanced by some very unusual phenomena, which we'll talk about in a little bit of detail. If we go into too much detail, it'll take a whole night just to talk about TEP. But the bottom line is it's fundamentally different than almost all HF propagation. Uh, this is going to be hopefully less than an hour presentation. And we're talking about a topic here that's extraordinarily complex. So we're just going to scratch the surface. And for those of you who have a interest in diving deeper, the first place I always recommend is this book on the right-hand side, Radio Wave Propagation, Here to There by the NORL. It's a modestly priced book, and it's very readable. It's not written for uh, the highly technically oriented ham, let's say, with a physics or electronics background. From a propagation point of view, the ARRL handbook has an excellent propagation section. Several of us who have a good deal of expertise in propagation rewrote the propagation chapter a couple years ago, and it's largely intact today. And of course, antennas are where the money is made. You have to understand propagation to kind of know where to be and when to be there, but if you don't have the appropriate antennas, then things can get to be an unnecessary struggle. And the antenna handbook is the authoritative place for hams to go for that kind of information, and it's exceptionally well written. So, what about sporadic E? Well, during the last solar minimum, roughly during the period before 2019, so that was about 6 years ago, we had several years of really extraordinary sporadic E propagation during June and July. And that just happened to coincide with the beginning years of the FT8 digital mode. And it was really quite remarkable how much FT8 activity occurred during June and July in those first few years, right around 2019, and how much DX was being worked in the digital modes. It was really quite remarkable. And even those of us who had a good deal of knowledge about 6 meter sporadic E propagation were astounded by what we were able to observe and the amount of activity that was attracted by the FT8 mode when it appeared on the air. And of course, as we all know, that digital mode has really transformed the 6-meter band and all the DX bands for good and for not so much good too. But it's that horse is out of the barn, and it's not going back. Only those stations in the United States located in the very most southern parts of the 48 states can operate 6 meters without sporadic E. In almost every case, we need access to sporadic E in order to work the trans-equatorial propagation modes that I'll talk about in a little while. And the further north you go in the United States, like along the Canadian border, the less and less reliable sporadic E is, unfortunately. It tends to be most reliable the further south you go, and it's especially reliable in June and July. This presentation will focus from a sporadic E point of view strictly on propagation from the lower 48 U.S. states. The very, very southern part of Canada is similar, but it's not as frequent or as reliable as it is in the U.S. And by the U.S., I refer in particular to the 48 U.S. states. Things are even worse in Alaska, and Hawaii is even better because it's in the tropical zone, and 6 meters is much more reliable in Hawaii than it is in the 48 states. Oddly, and for very complex reasons that I can't get into in any detail in this presentation because I don't have enough time, mid-latitude sporadic E in the southern hemisphere is similar in most respects, but it has some very unusual, unique characteristics that unfortunately I don't have time to cover in this presentation. But for those that are interested, you can Google sporadic E propagation in southern hemisphere and learn about some of the unusual aspects of sporadic E when you get down into southern Brazil and Argentina and New Zealand and southern South Pacific. And there are some other forms of sporadic E propagation that are unique but not covered in this presentation, and I'll just mention them just in the interest of completeness. Sporadic E occurs every day when you're within about 600 miles of what's known as the magnetic dip equator. What did he say? The magnetic dip equator. What the heck is that? Well, from a propagation point of view, the magnetic field of the Earth has a huge impact. And that's especially the case when the magnetic field, as it passes through the ionosphere, when it's exactly parallel to the surface of the Earth. And that area of the Earth's magnetic field in the ionosphere that is exactly parallel to the surface of the Earth has this unusual name, magnetic dip equator. So, and I'll show you a map in a little bit that shows exactly where that is. So in the Western Hemisphere, it's over Brazil for the most part. It's a big country. And if you're within 600 miles, more or less, of the magnetic dip equator, you get sporadic E every day. Every day. Unfortunately, it's in the Western Hemisphere. Well, in fact, actually everywhere in the world. You're in areas of the world where the amount of radioactivity is limited. So the ability to actually use it is not like we experience in highly populated areas like in Europe or like in the 48 states or in Japan. But nonetheless, it's what's known as equatorial E is there every day. And then there's another form of sporadic E, which is known as auroral E. And this is really rare, but when it occurs, it's spectacular. And my only QSOs from my QTH in Maryland to Alaska were via this mode known as auroral E. And unlike the normal auroral backscatter propagation, auroral E, at least as I experienced it on just a couple of nights, it sounds just like any other nice, clean 6 meter propagation. It doesn't have all of the auroral buzz and all that sort of stuff. It was very clean, and I worked several Alaskan stations near midnight on a couple of nights, and that was, about 25 years ago. And it was not by schedules. Fortunately, there were a few stations in Alaska that knew about this form of propagation, and I was tipped off to it by my neighbor W3UR and got on there, and son of a gun, there they were, a couple of nice, strong Alaskan stations after midnight. This mode of propagation, auroral ES, auroral sporadic E, normally referred to as auroral E, is not related to auroral backscatter, but it does occur during periods of very high K index. In other words, when the aurora might be present, but it's not auroral backscatter. It's auroral propagation directly through the auroral region and then scattered back from it. Okay, so let's get back to the main part of the presentation and not some of these other interesting but not very relevant because they don't occur very often in the case of auroral sporadic E, or it's not relevant to us in the United States if it's equatorial. So let's take a look at a little cartoon that kind of shows what's going on at mid latitudes with sporadic E. The longest distance propagation by sporadic E occurs when you're operating very close or just above the sporadic E maximum usable frequency. And during that period, around solar minimum, around 2019, boy, we had some really incredible openings from the East Coast all the way over to Japan on many nights during June and July. And my neighbor worked into Taiwan. It was quite remarkable. And also during that period, there was quite a bit of activity in the Indian Ocean. And I worked 3B9, which is a very, very long distance from here. And I also worked into Kazakhstan, right on the border of China, all by very long distance sporadic E propagation. So let's look at some of the characteristics. Number one, very importantly, from the point of view of antenna selection, the angle of radiation or the elevation angle is almost always below 8 degrees. So any radiation above that angle is pretty much wasted. So the design of whatever antenna you use wants to get most of that radiation down below 8 degrees. But you don't have to get it much below 8, but then I'll show you some statistics later about that. The exact nature of what causes the very long distance of sporadic E that we experience mostly in June and July is not very well understood. It's believed to be chordal hops between areas of sporadic E ionization. So the propagation is basically from wherever you are up to a sporadic E cloud or a patch. Either terminology is okay. And then from that point, proceeding over to another patch, and then yet another patch, and then coming back down to the ground up to 15,000 kilometers away. And boy, some of these days when this propagation is present, it's just incredible. The propagation can last for very long periods of time, surprisingly long. Other times, frustratingly, it can last for seconds. And with the FT8, we've become more familiar with that, where sometimes propagation doesn't last long enough for us to complete a QSL, but more often than not, it does, thankfully. So a lot of hams, when they first become active on 6 meters, first become familiar with sporadic E by the one-hop sporadic E that occurs every day in June and July, and that covers distances from 1 to 2,000 kilometers from the east coast of the United States. That takes us just into the northern part of the Caribbean, Cuba and Puerto Rico. And then beyond that, we need another hop. Oh, and let me mention something about the way I do presentations. There's so much data on these slides that I don't attempt to read the slides. The slides will be made available afterwards, and people can study them if they wish. But don't get too frustrated if I don't call out all of the topics on each slide, because if I did that, it would take me another hour or two to cover every topic in detail. But I try to prepare the slides in such a way that when you have time after the presentation, you can dive into them in more detail if you wish to do so. So for double hop propagation, which is probably the most common form of long distance propagation, so that's for sporadic E, that will take us across the entire extent of the United States. There are two common modes of double hop. One involves an actual reflection from the Earth. So if you're propagating from the west coast of the United States to the east coast, that would involve a hop that takes you back down to the ground somewhere around Kansas, and then back up to a sporadic E cloud and back to the ground. But the more efficient mode of this propagation actually uses a chordal hop from one sporadic E patch to the other and doesn't come back down to the ground at all. But then there's the really interesting form of sporadic E, mostly in June and July, that takes us halfway around the Earth in some cases. Now, there's what I believe is an undeniable relationship between the solar cycle and the frequency of sporadic E. We had long distance sporadic E on many days during the solar minimum years, and during the solar maximum years, and we're just ending that period now. Long distance sporadic E still occurred, but it was much less reliable. And in a couple of years, we'll be well beyond solar maximum, and I'm expecting to see more and more long distance sporadic E at distances up to 15,000 kilometers during June and July again. But hopefully this coming season in 2026 will be better than we've seen in a few years. Only time will tell. Now, you'll notice on this slide, I specifically refer to the Yagi on the left-hand side in Maryland as a 50-foot high Yagi. And that turns out to be about the best height you can use on 6 meters for long distance sporadic E, and I'll talk about why that is in a little bit. So this cartoon attempts to simplify an incredibly complex topic, and that is, why is sporadic E so different? Well, first of all, and very importantly, the mode of ionization is totally unrelated to the ionization that we experience on the HF bands every day. The ionization we experience on the HF bands is caused by ionizing radiation from the sun, but sporadic E has nothing to do with that. It's caused by high temperature entry of tons and tons of metallic micrometeoroid dust into the atmosphere. So many of us have seen shooting stars, and that's what that is. Most of the shooting stars you see are tiny pieces of dust that heat up to very high temperatures and emit light when they heat it up like that. And sporadic E has the same source. they're micrometeoroids, dust that enters into the lower atmosphere in what we call the E region of the ionosphere, and create free electrons. And the electrons are what ultimately cause the propagation. You wind up with patches of ions and electrons that were released by the high temperature ablation of tons and tons of metallic micrometeoroid dust. But that's not enough. Something has to happen in order for those electrons to form very dense patches that have an MUF of 6 meters and above. And there's a couple of very complex things going on in June and July that caused this compaction of electrons and their associated ions into patches of ionization. Very important is wind shear above and below these patches of free electrons. And those wind shears cause the electrons and ions to occur very much more densely. And they're also forced, the electrons are forced towards the ions by a force known as a Coulomb force. I'm not going to get into a detailed discussion of that. If you're interested, you can Google it. And they're also concentrated by a force that occurs in the E region known as Lorentz forces. And again, I'm not going to get into the details there. It will take too much time. But these are all of the things that have to happen in order for sporadic E to occur. Not surprising that it's sporadic. Everything has to be just right. It's really a miracle that it occurs at all on the magic band. These tidal winds that cause these wind shears reach their peak amplitude from June through mid-July, and that's why sporadic E has its most intense and most reliable occurrence during June and July. It's because of winds, so it's weather. So there's yet another thing that is a very important, necessary contributor to sporadic E, and also sitting at the top of the atmosphere at the lower edge of the sporadic E clouds. There are also tides and traveling disturbances, and those also cause increased density of these sporadic E patches and tend to create a global concentration. And it's really quite remarkable. These very long distance sporadic E propagation periods that occur in June and July, there's a tendency for them to occur in 2 days in a row. Not reliably, but it's a good idea if there's a really good day of propagation to pay attention to the next day because it might happen. But there's no predictability to this. It's just something you have to be aware of, the possibility that if you have a really good day, you might get another really good day the next day, but there's a probably equal chance or more that you will not. This is kind of an interesting chart prepared by some scientists, I believe it was in Norway. So what does this try to say? Well, first of all, the colors on this chart represent occurrence rate. It's tempting to look at this chart and think that it relates to MUF or something like that, but it's not. And it uses the colors of the heat scale to represent the statistics of sporadic E occurrence. What this chart tells us is that sporadic E is most reliable around 10 a.m. at the location of the sporadic E patch. So they tend to be one time zone to our east or one time zone to our west. We're not so interested in a sporadic E patch that occurs directly overhead. So around 10 a.m. is the best time, or the most reliable time for sporadic E in June and July. But it's fairly reliable from dawn all the way until about 3 p.m. or so. And then the statistics repeat in the evening hours, starting around 5 p.m. And there's another period of sporadic E activity that peaks around 8 p.m. to 10 p.m. at the location of the sporadic E patch. So that's tends to be 1 hour earlier than us if we're pointing west. And this is the sporadic E patches that gives us access to Japan, for example. So another interesting thing also is that the altitude at which these sporadic E patches occurs tends to drift downwards as the day goes on until about 4 p.m. local time under the patch. And then it regenerates in the evening back up at about 110-kilometer altitude and then gradually drifts down until it recombines with oxygen atoms, mostly when it gets down below 95 kilometers. So this is what causes the 12 and 24-hour periodicity of sporadic E that if you're very active on 6, you may notice. And the most reliable time is in the morning, but it still can be quite good in the evening as well. This is another statistical look at the occurrence of sporadic E. This shows the average daily meteor count through the year, and you can see here that the average daily meteor count peaks between late May and mid-August. So this corresponds very precisely with the count of micrometeoroids, and there's a very distinct peak during June and July, and a very distinct decline as the month of August proceeds. So in the blue color, that's the count, that's the meteor count, and in the brownish color is the average daily what's called the critical frequency of the sporadic E layer, and you can see that the critical frequency of the sporadic E layer is highly correlated to the meteor count that peaks in June and early July. And yet another way to look at the occurrence of sporadic E is the normalized meteor count rate. And interestingly enough, that occurs right around sunrise. But one other aspect of sporadic E is that once the sporadic E ionization occurs, it tends to be very long-lived. Recombination of these metallic ions does not occur very rapidly like it does in the HF bands for normal F2 propagation. In the HF bands, for sporadic E propagation of these metallic ions, once that ionization occurs, the ionization can last for as much as 24 hours. So even though the peak influx of metallic meteoroid dust occurs in from about 4 to 8 a.m., in other words, from sunrise in the ionosphere, not sunrise on the ground, sunrise in the ionosphere, the peak influx is from about 4 to 8 a.m., and then it gradually declines. And then there's another peak that occurs in the evening, and that's related to that second peak. And I'll leave the rest of these details for anyone who wants to read these slides afterwards. But it's amazing how many complex factors are at play during June and July that affect sporadic E. So let's get away from the propagation details for sporadic E and think about some of the easily observable basic characteristics of 6-meter sporadic E propagation. Those of us who operate on 6 meters are very familiar with most of these highly observable characteristics. One is that it's the sporadic E propagation on 6 meters tends to be highly spotlighted. And that's because these sporadic E patches tend to have an east-west width of 50 to 300 miles and a north-south width of about 50 miles or less. And if you're, it's very common to hear maybe some ground wave propagation from a station that's a few hundred miles away, enjoying some amazing sporadic E propagation for 1,000 miles away, and you can't hear a trace of it because you're outside of that spotlight. And the same thing happens sometimes when you might be in the center of the spotlight area, and your friend who's a few hundred miles away can't understand why he can't hear a thing. But it's just the nature of sporadic E to be highly spotlighted because these patches are limited in their extent. 6-meter MUFs get up to 50 megahertz every day in June and July, but not everywhere and every day. But somewhere in the US, and usually in many places in the US, the MUF exceeds 50 megahertz during June and July. This happens to be the time of year in October through early November when sporadic E is least common. But it still occurs, but very, very, very sporadically, and tends to be very, very brief. This long distance sporadic E propagation that can take us halfway around the world some days occurs in many days from early June to mid-July, a few days in late May, a few days in early August, and then it's kind of gone. And then we have a secondary period of long distance sporadic E that tends to occur in late December and early January, but it's much less reliable than the June-July one. But even though it's less reliable, it can still lead to some pretty incredible propagation. But boy, you've got to be on your toes to catch it. It's a good idea to have good relationships with some of the other 6-meter DXs in your area so that when the band is open, that they'll give you a telephone call to let you know something is happening. 6-meter sporadic E propagation is always true great circle azimuth, very, very rarely skewed. If it is skewed, it's much more likely to be skewed if you're down in the Caribbean. But at mid-latitudes, like in the 48 U.S. states, it's always true azimuth. And the preferred antenna is about a 3 to 6 element horizontally polarized Yagi at a height of about 50 to 60 feet. 70 feet is okay, but only for DX. It's too high really for VHF contesting, but of course it'll work. But if you have the freedom to make a choice of the height of your antenna on 6 meters, 50 to 60 feet seems to be about the best choice. 25 feet is a workable compromise height, much less than 25 feet. It's difficult to work long distance propagation at heights below 25 feet, especially if you're in an urban area where there are all kinds of buildings and obstructions at the same height as your antenna. You really want your antenna to be up above all the local clutter. If you're in a densely populated area, for example, you really want to get up above all that. And you also, if you're in an area near very dense forests, not just the light kind of forestation you find in populated areas, but if you're near very dense forests, you'd like to be at least 1,000 to 1,500 feet away from those very dense forests. For those of you who operate away from home during VHF contests or expeditions to rear grids, a really good thing to do for portable operation is to find a location that's on the side of a sloping hill. That can reduce the angle of radiation for a very low antenna. It's kind of inconvenient. It's very inconvenient if you're operating portable to put a 6-meter beam up at 50 feet. But if you can put it up at 25 feet on the sloping side of a hill, then you can get quite a good benefit. but that slope has to extend more than 1,000 feet in distance to really get a lot of benefit from it. And in terms of the variability, this very frustrating variability of sporadic E, as I mentioned, it occurs every day in June and July, but not everywhere and every day. Fairly reliable sporadic E begins during mid to late May, and then it gets frustratingly unreliable once we get into August. The sporadic E, as I showed you in that more detailed chart, tends to begin at dawn at the location of the sporadic E patch. So if we're beaming, let's say, to the east, dawn at the sporadic E patch would be just before sunrise at our location. It's not very reliable at that time, but as time goes on, the sporadic E propagation becomes more and more reliable until we get to about 10 a.m. at the location of the sporadic E patch, and then gradually the reliability declines. But you're more likely to have really good propagation in mid-morning and early evening than you are at noontime or 1 p.m. But this is statistical, so there'll be some days when the actual occurrence will be better in the middle of the day than it is at other times. But for the most part, mid-morning and early evening are the best, most reliable times. But you really have to be on your toes on 6 meters. The duration of propagation lasts anywhere from seconds, too short to complete FT8 digital QSOs. But on other days, the propagation can seem like you're on 20 meters and the propagation just goes and goes and goes. And then finally, after a long period of amazing 6 meter propagation, it will die, and you might not have that happen again for the rest of that year. These sporadic E clouds drift south to north, and they're forced to follow magnetic field lines. So in North America, they tend to drift from south and slightly to the west as they drift northwards. So let's say they drift sort of north-northwest over most of the United States, and they slowly drift. So why is that important? If you're listening to a friend of yours working sporadic E, let's say he's 400 miles south of you, but you can't hear a thing. If that sporadic E persists for an hour, you may very well be right in the middle of the very best part of that propagation, about an hour after your friend 400 miles south of you. So it pays to watch what's happening to propagation, even though you can't hear it, but maybe you're aware that stations to your south are experiencing it. Unfortunately, there is extreme day-to-day variability. About the only slightly reliable aspect of this is that when you have a really good day, there's a small but definite chance that the next day could also be good. There's also extreme variability between the morning and the evening. So if you have really good propagation, let's say from the west coast of the US to the east coast of the US, or maybe even into Europe in the morning, that does not mean that you're going to have the same experience in the evening to Japan. There's a not very good correlation between the morning and evening sporadic E propagation. So don't get discouraged. If the morning is poor, the evening propagation could be incredible. Very highly variable and extremely unpredictable. Back when I prepared this presentation a few years ago, there was a lot of hope that F2 propagation across the Pacific and across the Atlantic was maybe going to occur reliably like it did 20 years ago. But unfortunately, this cycle didn't prove to be that reliable. We had occasional F2 propagation across the Atlantic, but it was very, very infrequent. We had a few days in early November a few years ago of F2 propagation, but it didn't last long, and you had to be really lucky to be there at the right time and the right place. solar flux index had to be well above 200 almost every day, and that was not very common, except during early November during 2023. It didn't repeat very much at all in 2024, and I don't think we're experiencing much of any F2 propagation this year, except for TEP related. So let's hope that this coming June and July of 2026 that it's better than the sporadic E was during the very peak years of the solar cycle, and there's a chance that that'll be the case. But I think the probability is very, very good that as we approach solar minimum, it's about 5 or 6 years away, that sporadic E in June and July could be much more reliable than we've experienced over the last couple of years. So what about this thing called trans-equatorial propagation? Trans-equatorial propagation is F2 propagation. It's very, very much related to the F2 propagation we experience every day on HF, except it relies upon enhancement of the F2 region by some very amazing physics, which I'll talk about in a little bit. Unfortunately, the physics associated with trans-equatorial propagation is also frustratingly sporadic. So if you have a really good day of enhanced trans-equatorial propagation, it's not necessarily true that the next day will be equally good. Or on the other hand, it could be even better. TEP also tends to be correlated with the solar cycle. So even though, for example, over the last week, we've enjoyed quite a bit of TEP propagation, actually, since we've enjoyed it since late August, but it's gotten to be especially good over the last week or so. It's also correlated to the solar cycle. So keep in mind that TEP is an enhancement of basic F2 propagation. So, and what it tends to do is it takes the MUF, maximum usable frequency of the F2 propagation, and enhances the MUF by about 25%. So if the if propagation is solidly open on 10 meters to South America, I mean really solidly opening, solid openings into South America on 10 meters, then there's a very good chance that the enhancement that I'll talk about in a little bit may very well bring that F2 propagation up into the 6-meter band. Unfortunately, during solar minimum, the basic MUF of F2 propagation that we experience on 10 meters is not high enough for very frequent TEP propagation. So TEP, while it occurs quite reliably at this time of year and in the springtime, after a few more years, it's going to be less common. So enjoy it now while you can. So we're in the part of the solar cycle where TEP tends to be fairly reliable on 6 meters, but over the next couple of years, it'll start to become less and less reliable, and it'll be very unreliable during solar minimum. But on the other hand, near solar minimum, sporadic E gets to be very reliable. So we get much less TEP. TEP becomes rare at solar minimum, but sporadic E becomes more reliable. So we get a little of each. What about the solar flux index? It's a measure of ionization. From an HF point of view, we tend to like to see solar flux indices above 160 for very reliable 10-meter propagation. Now, during the month of August, there are other aspects that tend to optimize propagation. So during October, 10 meters, as it was during the CQ Worldwide Sideband Contest a couple of weeks ago, was very good, even though the solar flux index was only around 140. But October tends to be a magic month for propagation, and it was that way in the CQ Worldwide Contest 2 weeks ago. Unfortunately, now this forecast that's shown here in this graphic is from the NASA Marshall Space Flight Center. They update that forecast on about the 5th of every month, and the website is shown here. You don't have to worry about writing the stuff down because these slides will be available. And now we are in this decline where the solar flux index rarely gets up to about the 160 level now, and more commonly sits down around 100 to 120 at this part of the solar cycle. And there's even a few days when it dropped below that, like it did 3 or 4 days ago. There are actually two solar cycles at play. The solar cycle of the northern hemisphere of the sun is a distinctly different solar cycle than that in the southern hemisphere. They tend to be correlated, but they can be offset by as much as 2 years. And this is what causes some solar cycles, like the last one, solar cycle 24, to have two peaks. So in this case, you can see this was most recently updated last year. And you can see for the northern hemisphere of the sun in this light blue color, it reached a sunspot number of only about 60, but at the same time, the southern hemisphere, shown in this purple color, had a sunspot number about twice as high, and then the combined northern and southern hemisphere peak was up around 160 and 170 last year. It's not reliably that high this year. So what about this solar cycle compared to all the other solar cycles? Well, this shows all of the solar cycles since cycle 1, and they're all normalized, so solar minimum occurs at month 0 in this chart. So for all of the sunspot cycles, solar minimum is right here. And one thing you'll notice about the very strong sunspot cycles, like solar cycle 19, the legendary one that reached its peak in 1957, 1958, notice how the very strong cycles, these cycles right here, they climbed from minimum to maximum in 3 to 4 years. And the weaker ones, like especially solar cycle 24, 11 years ago, climbed very slowly. And when you see that very slow climb, it always means that you're not going to have a very strong cycle. And one more aspect that's important statistically is that 68 months after solar minimum is when every solar cycle was in decline, after month 65. And we're at about month 70 in this solar cycle. So you'll notice for every solar cycle, 70 months into the cycle, they're all in decline. And of course, if you're active on the bands at all, you're well aware that we're no longer at the peak of sunspot cycle 25, but we're still getting lots of good propagation. Another way to look at what goes on in the sun during the solar cycles. This photograph on the right side is a very clever photograph by a couple of photographers in Eastern Europe. And what they did is they took snapshots once a day of sunspots during the course of the year. And you can see very clearly that the southern hemisphere of the sun during the solar cycle, and this was last year, I believe this image is from, had many more sunspots. There were some larger sunspots in the northern hemisphere, but the majority of them were in the southern hemisphere. And taking a look at a chart rather than an image of the sun, you can see in red that the southern hemisphere of the sun had more sunspots than the northern hemisphere. This is January 2025, and there was some hope because the northern hemisphere, shown in green, started to show a little bit of increased activity in January. Unfortunately, that was very short-lived and didn't continue throughout the year. In terms of forecasts, This is the Space Weather Prediction Cycle Center's forecast in July 2025. The most current one is very much similar to this, and you can see that they're forecasting continual decline of solar cycle 25. We're now right about at the end right now of the solar maximum period, and entering the steady decline towards solar minimum. But we've still got many months of good propagation and many months of 6-meter TEP propagation as well before that becomes rare. One unfortunate aspect about where we are in the solar cycle. This is the Marshall Space Flight Center's forecast of the A index. That's the index that measures disturbed propagation. And so here we are in the middle of 2025. And what they're forecasting with the green line is the main one to pay attention to. That's the 50 percentile propagation, 50th percentile likelihood line, is that we're in a period of the sunspot cycle that tends to be more magnetically disturbed. So we have more disturbed days. We're in the middle of one of those days today. But when we get to about 2028 and declining towards solar minimum, then these disturbances become less frequent. Unfortunately, F2MUFs become lower, and TEP also becomes less common during this period from the point of view of a 6-meter DXer. So we're still at a very good time of year for 6-meter time of the solar cycle for 6-meter TEP, but that's probably only about 2 more years of reliable TEP before it starts to become very sporadic. It's a very complicated chart. What it shows is coronal mass ejections, and in particular fast CMEs that are the most powerful. They're the most energetic. Fortunately, CMEs have I'll call it a beam width, a relatively narrow beam width. So when the coronal mass ejections, these can be billions of tons of charged plasma, explode from the sun. The beam width of that explosion is narrow enough that most of them miss the Earth. It's a fortunate thing, because when they have a direct hit on the Earth, the effects on propagation are extreme. So the bottom line of this very complicated chart is that near solar maximum, which is where we are now, we're about 2 years after solar maximum right now, these fast CMEs are the dominant cause of severe propagation disturbances. And then as we get towards solar minimum, the fast CMEs still occur, but they're a lot less frequent, about half as often for strong CMEs during solar minimum, and about 30% as often for the very severe ones during solar minimum. So CMEs are the really nasty cause, but thankfully, most of them miss the Earth, and the ones we do experience are mostly grazing the Earth's magnetic field rather than a direct hit. But you'll know when you've got a direct hit because the bands are really, really degraded. Okay, so let's talk about trans-equatorial propagation. I'm not going to read this slide. You can go back and read it later. TEP propagation is really incredible if you ever get an opportunity to operate from the Caribbean. It occurs just about every day during the 5 or 6 years near solar maximum. And a couple of years ago, when we were really near the peak, the hams in the Caribbean and Central America were having just a field day of long path propagation, big long duration openings to Japan from the Caribbean. Most of that is gone now, but it was really incredible for the people in the Caribbean 2 years ago, and a little bit this year, but nowhere near like as it was 2 years ago. So there's a really, really good article about Trans-Equatorial Propagation. I highly recommend this one. It's very readable. Last I looked, it was still on the web. It was written by Jim Kennedy, K6MIO, who's a very well-known expert on 6-meter propagation. It's well worth reading. So I showed you that little complex graph that showed all of the incredible aspects that have to take place for sporadic E propagation to occur. Recall, sporadic E propagation is rooted in the ablation of micrometeoroids as they enter the lower atmosphere. Well, it's a completely unrelated process that takes place for enhancement of F2 propagation that affects 6 meters, and it's called the plasma fountain. What in the heck is the plasma fountain? Well, it occurs near the magnetic dip equator. That's the, if you remember, that's the place where the Earth's magnetic field in the ionosphere is exactly parallel to the surface of the Earth. And there's a number of very complex processes that take place. I don't have time to describe those in detail in this short presentation, but you can read about it on the web by just Googling for some of these terms like the E-regional equatorial electrojet and the trans-equatorial propagation plasma fountain. But what's happening here is that above the magnetic dip equator, there's an upwelling of electrons that propelled vertically above the Earth's surface, up above the F2 region, until gravity takes effect and forces these electrons to come back to the Earth. And they come back to the Earth about 15 degrees north and south of the magnetic dip equator. And very specifically shown here, in South America, the magnetic dip equator passes over Brazil. And for our TEP propagation into Argentina, which tends to be very reliable, the geography basically is that the electrojet originates over western Brazil, goes up above the F2 region, gravity brings it back down to the Earth over Venezuela and Bolivia, and then so the propagation from let's say Haiti or Puerto Rico goes up over Venezuela, crosses from one enhanced area of the F2 region across without going back to the Earth to another enhanced area over Bolivia, and then comes down in Buenos Aires. And that's why we hear so many LU stations on 6 meters during the years near solar maximum, especially in the spring and the fall. And there's a lot of activity from South America on 6 meters this week. This is a map that shows the location of the magnetic dip equator. Notice an odd aspect of that. The magnetic dip equator, where the Earth's magnetic field is parallel to the Earth, it doesn't go directly east-west over South America like it does all over the rest of the planet. It runs kind of northeast southwest, which is kind of fortunate because South America is not directly south of North America. It's about one time zone to the east, so this is a very fortunate thing that gives us a very reliable TEP propagation, especially into southern Brazil, Chile, and Argentina. And I'm not going to read the rest of this chart. You can read that later, and if you're really interested, you can research some of these topics on the World Wide Web. The peak current density tends to occur near the equinoxes at 11 a.m. to 1 p.m. local solar time. What in the heck is that? That is the time under the let me just go back to that chart. Under these ionization crests. So the very best time is tends to be early afternoon in the U.S. With these crests located just to our east. So that's the time you really want to be prepared. There is usually in the early afternoon, and then there tends to be another peak in the evening, but it's not as reliable. The afternoon peak is by far the best one. It tends to be early afternoon until about 3 or 4 o'clock in the afternoon for the most reliable TEP propagation. And this is a look at a map that shows what's happening. So remember the magnetic dip equator I talked about, which is where the Earth's magnetic field is exactly parallel to the surface of the Earth, the magnetic field in the ionosphere. So it runs from northeastern Brazil and then, of course, through the center of Peru. And then these ionization crests tend to occur up over Ecuador and Guyana. And then in the southern part of South America, the crests tend to be over Bolivia and the center of Brazil. So we tend to have propagation via TEP mostly into Chile, Argentina, Uruguay, Paraguay, and the southern part of Brazil, and even some days into VP8. We need a sporadic E hop usually in order to get into VP8, and on some very, very, very lucky days into the very most northerly part of Antarctica. And this is a look at TEP propagation as observed on PSK Reporter, and you can see the TEP propagation, especially from the southern tier of the United States down into Argentina, Chile, Paraguay, and so on. But you can also see this pesky TEP propagation from Europe that we have to compete with also at the same time. But TEP doesn't end with that. It isn't just to South America. There's another form of TEP called oblique TEP that instead of running north-south tends to run to the southwest or to the southeast. And we've had quite a bit of that over the last week into sub-Saharan Africa on 6 meters. It's been frustrating in some respects because the propagation has been unreliable. It tends to be very spotlighted, but nonetheless, it's been pretty amazing that some of the stations in the United States have been working into 7Q7, Malawi. They've been working into 9J2. They've been working into some of the other countries in West Africa. But boy, it's the magic band at work. You've really got to be in the right place at the right time. I've had some very interesting QSOs via oblique TEP to 3D2AG and E51EME, FK8CP, who's still very active on 6, VK4 and ZL. But once again, the effects of TEP are more widespread than just deep South America. You can have propagation via just the northern TEP zone, what I call the Caribbean F2 zone. So you get a single hop up over Colombia and Brazil, and that brings propagation to Ecuador, Peru, the northern part of Brazil, and PZ and 8R1 and those areas. But it's the same type of propagation, but it involves, and I'll go back to this map, it involves propagation only off the northern F2 equatorial ionization crest. So from North America, reflecting off of this crest and then into the central part of South America. Doesn't involve the southern crest at all. Okay. And this is QSO. I've had several QSOs with D2UY. He's located in the South Atlantic TEP zone, and this shows where the propagation is taking place. So sporadic E hop into the northern ionization crest, crossing the magnetic dip equator, and then into the southern area. One of my favorite tools, not only for 6-meter propagation, but also for HF propagation, is PSK Reporter. This chart happens to be for 20 meters, but there's a lot of reporting on PSK Reporter on 6 meters, and it's a wonderful tool. Even if you're not a digital operator, you should use this tool because it's telling you what's going on with propagation right now. I like to call that nowcasting. And you can use it not only to look at other DX stations, you can also look at it to see where you are being heard. So if for example, you're calling a DX station in Africa and you want to know if anyone else in Africa is hearing you, you can go to PSK Reporter and you can see where you're being heard. Or if the band is open to Europe, you can see if there's any propagation that extends further east into Eastern Europe or the eastern part of the Mediterranean. It's a very powerful tool. So that's the end of my presentation. I know it's been like a fire hose. I'm always willing to answer questions. My email address is shown here.